welcome. We'll get started in just a second to continue on lecturing where we left off. And again, as always, if you do have questions, feel free to type them in. I will get to them as I'm lecturing and try to answer them. And again, here we're going to lecture to try to, kind of keep on pace here, at least try to get through some of the material that's going to be on the next lab. So hopefully you'll have a better understanding when that lab opens up as to how to sort of do it. And, just kind of keep us on pace, especially since we have the exam next week to take as well. So we just want to kind of stay on pace here. So today's lab experience will be much like your lecture experience. There'll be some lecturing here through this chapter, and we'll talk about the lab and all that towards the end of it. So before we get going, again, was there any questions on any of the stuff that we were talking about in lecture? Be happy to answer that before we get going, if there is any questions about Ka problems, percent ionization. Okay, then I guess we will pick up. So we left off really talking about weak acids and sort of how to do weak acid problems. Again, because they are weak acids, that essentially means that they will set up that equilibrium, and also means that in order to truly be able to calculate the pH of that solution, what you really need to know is not the H plus concentration at the initial aspect of it, but you really do need to sort of figure out the H plus concentration at equilibrium. And so since it is an equilibrium, that's why we do need to do the ice table, because that is really what's going to help us determine what the equilibrium concentration of H plus is. And that essentially would be, when everything comes to equilibrium, how much free H plus you would have in that solution. And that's really how we get to the pH values and stuff like that. So again, it's a little bit more of a complicated sort of calculation than, say, the pH of a strong acid. And that, again, is because in a strong acid, there is no equilibrium that gets set up. It just 100% breaks apart. And pretty much what you have in that solution is all that H plus to begin with. And again, that's different than our weak acids, which for the most part mainly will stay together. So you have a lot of the whole acid still together in that solution, but will break apart into some H plus, and that's why we need to determine how much H plus that actually is. And what we have also saw in those examples that we did earlier, again, remember that you can't necessarily use pH to determine if something's a strong acid or a weak acid. Again, it just sort of determines how acidic that solution is. And as we saw in a couple of those examples, you technically, if you had a pretty good concentration of your weak acid, you can generate a fairly low pH. And if you had sort of a smaller concentration of that acid, you'll probably generate a little bit higher of an acidic pH and stuff like that. So where we're moving on to now is the opposite here. So we talked about sort of strong bases and how you calculate the pH, which, much like strong acids, they will 100% break apart into their ions. And from that, you can figure out the OH minus concentration. and that'll allow you to get to the POH and then to the pH. So when we deal with weak bases, it also will set up an equilibrium just like weak acids, which means just like weak acids, when we deal with our weak bases, it is also going to be an ice table situation. So we will have a KB value. Very creative here, B meaning base. So this is the equilibrium constant for a weak base. And it's just like all the other equilibrium constants, it's our products over our reactants. Also means that if we want to calculate the concentration at equilibrium, we are also, for these guys, going to have to do ice tables. Now, as we were talking about kind of earlier on this chapter about writing the actual equation, this is the one place where most people will actually put the water into the equation. And I recommend doing that as well, because sometimes people have a very hard time when they're like, okay, I got NH3. I'm not really sure what it is sort of on this side. So sometimes with bases, especially weak bases, it's good to put that water in there, because you know the base is going to accept the H plus. So you can kind of visually see the H plus going, and you can hopefully kind of visually see that is how we are able to generate the hydroxide. So in probably all of these cases, in terms of writing the reactions and stuff like that, like I said, with the acids, you can put the water in and you will get the H3O plus on the other side. But very common people will put the water in when they're writing the reactions for a weak base like we see here. The other important thing is, though, when you deal with these is when we get to our equilibrium expression, again, just like a normal equilibrium expression, as we talked about earlier, no liquids are solids. And that means that this guy does not find his way into our expression. So again, although people will always put the water in, you got to remember that you do not include it into the equilibrium expression. Again, it will have no effect on the calculation or anything like that. So I would recommend putting it into the equation so you can kind of maybe visually see where everything's coming from. But again, remember not to include it in the calculation. These problems are done just the same way as our weak acid problems. The only difference is when you look at the product side, you have here OH minus, not H plus. So when you go through your ice table and you solve it, when you solve for X, that is usually going to be the hydroxide concentration, which means you cannot directly get the pH from that. You first got to go to the POH. And then from the POH, you need to go to the pH by most often. So that's the slight variation in these type of problems when you're dealing with weak bases. Done the same way, you're going to do your ice table, you're going to solve for X. Again, you could try your assumption if it works. If it doesn't work, then you need to do the quadratic formula. And then when you solve for X, though, you got to keep in mind that, again, that is not the H plus, so you can't go directly into the pH. You got to first get that POH value instead, which I think is what just scrolled there on the bottom. Let's come back. There we go. The relationship is the same sort of relationship that we saw with Ka. As the Kb value increases, the strength of that weak base will also increase. Wow, it just wants to go forward, doesn't go back. And again, it's for the same reason. If we have that large value of K, that means we have more products, and more products means more OH minus, which technically would make it a stronger, again, weak base. And vice versa. If you had a small value of Kb, that means you should mainly have reactants and not as much free OH minus, which means it would be a weaker weak base, if that makes sense. Also, just like the Ka, anybody that is a weak base is obviously a much weaker base than a strong base, something like sodium hydroxide, potassium hydroxide, that little list that we saw earlier. Any questions on that? And also, like acids, you will not find a Kb value for a strong base. So you will not find a Kb value for a strong base. Again, for the same reason, a strong base, much like a strong acid, is going to head apart into those ions. And again, you will have nothing but those ions in that solution. It will not set up an equilibrium, and thus you would not have a Kb value. So much like your acid, if you see a Kb value associated with a base in a problem, you can assume that it is a weak base, or if you're able to find it on a table, you could assume it's a weak base. And obviously, probably a safe bet, if it doesn't have hydroxide in it, it might be a weak base. If it does have hydroxide in it, probably 9 times out of 10 it's going to be probably a strong base. So just like our weak acids, there's a table in your book which you again may have to reference in order to solve certain problems if they don't give you the Kb value. But again, you could obviously look them up, and on exams and quizzes, it obviously would be provided for you as well. So why don't you give this guy a go here, take a couple minutes or so, 5 minutes, and kind of work through it. Here we're looking for the pH of this solution. We see the Kb values given to us. So again, big neon sign there that says this is a weak base, which means you should do a ice table and solve for X. So we'll give you a few minutes or so, like 5 minutes, and give it a go, see how far you get, and then again we will go over it to make sure everybody's on the same page. If you do have questions, obviously during this time as well, feel free to type them, and I'll be happy to answer them. Okay, so let us take a look and see how everybody's doing. If you may not be done, just kind of progress through it. So again, we see that this is a KB, which tells us it's a weak base. So to figure out the pH, we do need to do our ice table, and we would want our weak base, which we're starting with, C2H5NH2. And again, here with your weak bases, it's good to maybe include the water. Again, because it's a base, that's where you could kind of visually see, which gives people sometimes a hard time, that it is going to accept that H plus. And when it does so, we will get C2H5NH3. I'll just add it at the end, Na plus. And then we will get our OH minus in this case. Any questions on the reaction or how to write reaction? So again, it's sometimes really beneficial to have the water there for the weak base. Normally 1.5 plus X here. I feel like I wrote that very far apart from each other. And when we do reach equilibrium here, (0.15 minus X, X, and X. Now, when you look at this table, you will notice that I did not write anything there where the water is. Yeah? And again, as we talked about, the water is a pure liquid. It's not going to be involved in the calculation, not going to be in the KB value here or expression. And I find it is best not to put anything here. Oops. Wow, that freaked out. Not to put anything here. Again, because sometimes when people put stuff there, they want to try to use it in the calculations and stuff like that. So best rule of thumb is to keep it open and clear, then you don't have to worry about it. Our KB expression in this case would be our products, which is our C2H5NH3 plus times our OH minus divided by our reactants, which is C2H5NH2. Again, no water involved here. We're going to do our 5.6 times 10 to the minus 4. So putting into there our values, we get x squared over 0.15 minus x equals 5.6 times 10 to the minus 4. We could assume here that x is equal to 0. And x squared is 4. Now, if we do that and solve for x, 0.15 times 5.6 to the minus 4 gives us a square root. And that gives us something like x equals 0.00917, which if we divide it by 0.15, and times it by 100, sadly, based on our 5% rule, we get like 6.1%, which is very close, but we're going to follow that rule, which again would mean in this case, sadly, this is a bad assumption. So again, if you don't want to worry about it, it does work in a lot of cases, but you know, if you don't want to worry about it, you can just go straight into the quadratic, but I would still give it a try. It doesn't take that long to do it. And if it works, it's usually a lot quicker. So that means we're going to have to come back and solve it using something like the quadratic. And if you do some distribution of our original guy over here, any questions up until that point there? Now, just like before, in this case, because it's a base, correct number, because that would give us a negative. The other number should be minus 0.87. Again, our calculation is 0.887. And if you do that, Gets you a pOH of 2.05. Then our pH would be our 14 minus our pH. And that should get us a pH of 1195. Which again makes sense because this is a base. 11.95 is a basic pH. And if for some reason you got confused and you thought this number here was the pH, again, you need to think about, does it make sense? And it should not make sense to you because basically you would have an acidic pH if you thought that was the pH. So that again would not make sense. So you want to make sure that you do get the pH in this case. Any questions on any part of the calculation? Again, hopefully you can see it is essentially the exact same calculation as what we did with our weak acid. The real main difference is here when you solve for X, it's not going to give you that H plus concentration, but that OH minus concentration. So first you got to get that pOH and then do a little subtraction of 14. Any questions on any of those steps along the way? And like I said, I would recommend in this case to leave the water into the reaction. But again, don't put any numbers underneath it in the ice table. That way you're not tempted to do something stupid. I'll just use the word there, stupid, yes, and put it into the calculation. Any questions on that? Okay. So those are weak base problems, which again are pretty much done the exact same way as our weak acids. So we have a weak acid, which has a Ka value, and we have a weak base, which has a Kb value. And just like we talked about with these guys, these are really just equilibrium constants, regardless if they say A, B, C, D, whatever it may be. So we can do something that we've done before. And if we add both of these reactions together, the A minuses will cancel out, the HAs will cancel out, and we are left with water. So this brings up a really important relationship between Ka, Kb, and Kw. Kw, again, is our 1 times 10 to the minus 14, like we saw earlier. This will allow you to solve for a Ka value if all you're given is a Kb value, and vice versa. If you have the Kb value, it will allow you to solve for the Ka value. And this is really important because there will be certain problems coming up very shortly. There will be certain problems where they will actually give you the wrong K value, in the sense you will be given the wrong K value. They'll give you the Ka value when you actually need the Kb value to correctly solve the problem, or they'll give you like a Kb value when you need a Ka value to correctly solve the problem. So this is a very convenient way using Kw, which is a constant in most cases. Again, most time we're assuming 25 degrees Celsius. So you could assume that it is 1 times 10 to the minus 14. And it's a quick way that you can calculate the other K value that you need. Again, if you're given sort of the wrong one. So this relationship here, you do need to know, and make sure you keep that in mind because you will use it in a good number of calculations in this chapter for sure towards the end. So what we're going to talk about next is a little bit of how you can sort of determine acid strength and sort of which acid is perhaps a stronger acid than another one. And when we look at how to do this, there are certain factors that's important in terms of what aspect you look at. in terms of acid strength. And the first type of acid we're going to talk about are these guys here. They have no oxygen. So this is like your HCl, hydrochloric, your HBr, your hydrobromic, or hydroiodic, and so forth. Yeah. And really, a lot of these guys are right here in our good table here, our periodic table. They're all in group 7 and the halogens, a lot of these guys. And you may think that, the overwhelming sort of thing that you may look at is electronegativity, which increases, right, as you go, which increases obviously as you go up there towards fluorine. And it is actually not what we look at when we look at sort of the strength of this type of acid. What we actually look at is what is known as the bond energy or the bond enthalpy. And that is the value, bond enthalpy. And when we look at the bond strength of these bonds, basically going down, group 7, is 500, the 427, 363 for HBr, and 295 for HI. That is the amount of energy needed really to break that bond, right? So when we would break that bond, you would need to throw in there, for example, 565 kilojoules of energy for every mole that you got there of HF. And as we go down, what we see is the bond energy actually gets smaller as you go down. And what that in terms means is for this type of acid, based on bond energy, the strongest acid is actually this guy right here, while the weakest acid is this guy here, based on bond energy, which is what you look at. And again, the reason for that is the really basic understanding of what an acid is, right? So an acid is something that has the ability to produce free H plus. Now, if you have this bond here, in order to produce that free H plus, you need to break it, which means in the case of HI, it doesn't take a lot of energy to break it, which means this H plus will come off easier. And because it will come off easier, that means it's able to produce more free H plus, and thus would be a stronger acid because it has the ability to produce more H plus. As opposed to when you get to HF, it's about 2 times the energy to break this bond, which means less of it is going to come off compared to HI, for example. And you'll get less H plus, which means because you're producing less H plus, the HF would be a weaker acid than something like HI, which can break that bond easier, liberating free H plus and being a stronger acid. So in terms of acid strength, it actually increases as you go down group 7 in terms of this type of acid. Again, the hydroiodic acid would be the stronger acid. Any questions on that? Okay, so then let's take a look at sort of how to compare acids that actually do contain oxygen. And this is what we see here, increasing acid strength as you go down, increasing acid strength to the right as well. If you look on the periodic table, that's from your book. And that's what we were just looking at there. Again, the stronger the bond here based on bond energy, the weaker the acid because it's going to be harder to liberate that free H plus. All right, now let's get to, so again, in our sort of order, HF is much weaker than HCl, HBr, and HI. These guys are considered strong acids, while this guy is considered a weak acid. because of that bond energy. Now, when we look at acids that contain oxygen, there is actually two different things that we will look at depending on the situation that we have occurring and depending on sort of the acids we're comparing. We may look at the electronegativity of the center atom. And just a reminder that electronegativity is the ability of an atom to bring electrons towards itself. It's what creates this sort of separation of charge, right, that occurs because of the difference in electronegativity. And again, the greater that sort of electronegativity is, the weaker this bond will become and allow it to basically break off. And the second thing that we may look at in these type of acids that contain oxygen is the oxidation state. And the oxidation state of that center atom, which is Z, again, the bigger the positive charge, the greater the distance, or the electrons will be separated in that OH group and allow basically that hydrogen to come off. So let's take a look at each of these sort of examples and see where we look at sort of which one we look at first. So when we look at an acid like this, which is HClO3 and HBrO3, it's basically the same acid. Each of the center atoms, the chlorine and the bromine here, they both actually have the same oxidation number. So just a reminder on how to do oxidation numbers is oxygen is typically -2, except when it's in peroxide, then it's -1, which looks like this. Everybody else is sort of their normal. So if we assign an oxidation number to this oxygen, it's -2. This guy is -2. This oxygen is -2. This hydrogen has an oxidation state of +1. So when we look at the oxidation state of chlorine, we have -6 and +1 gives you -5. So to balance that out, the oxidation state of the chlorine in the center is +5 in this case. Oxidation states, again, are not necessarily the charge that you normally associate with things. It is basically kind of the charge it would have if all the electrons in that molecule were transferred to the chlorine, for example. If we go about our guy over here, we would give a -2 to this guy in terms of the oxidation state. The oxygen here would be -2. This guy would be -2, and this guy would be +1, which means, again, in this case, the bromine has a +5 oxidation state. So when you have an acid that contains oxygen and the center atom has the same oxidation number, which is what we have here, it is at this point where we then would look at the difference in electronegativity. So the overwhelming thing that you would look at in trying to compare between two acids that have basically the same oxidation state, they're usually acids, just like you see on the screen, that pretty much look the same, but the center atom's different. We want to look at electronegativity. Now, in this case, when we compare the electronegativity of chlorine versus bromine, again, electronegativity increases as we go up in group 7. That means that chlorine is more electronegative than bromine. And what that essentially means is we already have over here, let me swap colors real quick. We already have over here, if you want to think about it, a partially negative charge. That's bad. We have a partially positive charge on the hydrogen and a partially negative charge on the oxygen. And if this guy here is more electronegative, what is going to do? It's already heading in this direction. But now, since it's electronegative, going to make electrons first, what that's going to cause positive side bond here, the hydrogen become weaker and weaker, and you're heading basically, and they're basically weakening that bond even more than it was originally. So in this case, when we are comparing two acids, same center, same oxidation state on the center atom, we want to look at electronegativity. And in this example, this guy would be the stronger, I'll get the right words here today, the stronger acid of these two. Any questions on that? So one type of acid that contains oxygen, everybody's got the same on the outside, different center atom, but that center atom has the same oxidation number. The way you determine which one is stronger is to look at electronegativity. The more electronegative the center atom is, the stronger the acid would be, because again, it's going to weaken that OH bond and allow that H to come off easier. Now, we can have a situation where we actually do have the same central atom, but everything on the outside is different. And that's what we see here. Here we have the same central atom on all these acids that have oxygen in it. They all have chlorine. So different than the acids we were just looking at here, kind of in this case, everything on the outside is different, but the central atom's the same. So in this case, because the central atom's the same, you can't compare electronegativities because they're all going to obviously be the same. So in this type of acid, what we look at is actually the oxidation number of the central atom. And the oxidation number of that central atom, the higher the oxidation number, the stronger the acid. So if we do oxidation numbers over here, just to remind you, again, -2 for our oxygen, +1 here. That gives us a -1, which means to balance it out like it shows there, the chlorine in this case would have a +1 oxidation state. That -1 is better there. And lastly, and 8 to get a calculator. 8 and which means we see that. So the strongest acid, as we can see, like it just popped up, would actually be this one. Would be the strongest. All the electrons to a lot easier. So here, the much smaller electron direction. It's a little bit harder for it to come off. So in comparison here, going from our perchloric acid to our chloric acid to our chlorous acid to our hypochlorous acid in terms of acid strength, our HClO4 is the strongest out of this group. Our HClO is the weakest. So that is typically how you could kind of use some different aspects of acids to compare which one is stronger maybe in a group, which one is weaker. So again, just to summarize, if the acid does not contain oxygen, the overwhelming sort of aspect that you want to look at is bond energy or bond enthalpy. Again, the stronger the bond energy for that bond, the weaker acid it would be. The lower the bond energy is for that bond, the stronger the acid would be. When you get into acids that contain oxygen, you can look at either electronegativity or you can look at oxidation number. You would want to look at electronegativity like we saw on the previous slide when you have an acid that basically looks the same on the outside but has different central atoms, but those central atoms both have the same oxidation number. Then you want to look at electronegativity. Again, the higher the electronegativity, the stronger the acid. The lower the electronegativity, the weaker the acid in the comparison. And the last way to look at acid strength is when you have the same central atom on all of the acids. Again, you can't use electronegativity in that case, so you have to look at the oxidation number of that central atom. And the one that has the higher oxidation number will be the stronger acid in that sense, in that group. Any questions on any of those there? So again, if you do have questions, please ask them. And now we are going to get to salts and what happens when we do basically react an acid and base together. So if you remember the basic sort of reaction that occurs when you take an acid plus a base, you basically get two things. You get water and you get a salt. And the salt here is really just an ionic compound. And remember that it's really sort of almost like a double displacement reaction that occurs. Oops. Sorry. Come back. I think I lost it there. Let's try that again here. Sorry. So our acid plus our base, I'm not sure where that just went, gives us our water and our salt. And again, our salt is an ionic compound. And in certain cases, the salt's really important because in certain cases, the salt will not have necessarily any type of effect on the pH of the solution. It essentially will not do anything. It will not further react or anything like that. And in certain cases, when we produce these salts, they will continue on and basically react. And when they do continue on to react, give me 1 second here. When they do continue on to react, what they're going to react with is what is there. And as you can see, what it is they're going to continue to react with water. And when they continue to react with water, that is when they can have the ability to produce maybe some more H plus. They may have the ability to produce some more OH minus, and they can have an effect on the pH of that particular solution. So the important relationship is something that we talked about earlier on. If you remember, there is a relationship between an acid and its conjugate base, where if the acid is strong, the conjugate base will be weak. And vice versa, if the acid is weak, its conjugate base will be strong. And the same relationship happens with a base and its conjugate acid in this case. And if we have a strong base, its conjugate acid will be weak. If we have a weak base, its conjugate acid will be strong. So this is exactly when we deal with salts, the important part is that relationship. When we say that the conjugate acid or the conjugate base is relatively strong, what we mean is it's not strong like it's a strong acid or a strong base. It's strong in the sense that it will want to continue to react once it's made, and it will want to react with water. So let's take a look at some salts which are neutral. And those are basically anything that contains an alkali metal or an alkaline earth metal, except for beryllium. That is essentially your group 1 and group 2 on the periodic table. And if you remember from our conversation earlier, that is where we have a lot of strong bases come from. Yeah. So like if you had sodium hydroxide, the sodium part of that is a neutral salt, or neutral ion, because it basically comes from sodium hydroxide and it very much will not react with water or anything like that. So when we have something like sodium chloride here, this salt probably came from the reaction of something like hydrochloric acid plus some sodium hydroxide. And what we produced was water and our sodium chloride. So really what we're looking at here is this salt that originated from a strong acid and a strong base, which means the conjugate base over here is going to be weak. Which means for it to be a neutral solution because none of that salt will continue to react. Now, if we take a salt that's different, like over here maybe. Let's take a salt like, for example, let's take a salt like sodium nitrate, not sodium nitrate, sodium acetate. Now, this sodium acetate, when it breaks apart, will break apart into sodium ions and acetate ions. And this salt, if you want to think about it sort of backwards, we'll just go this way with it, most likely came from the combination of sodium hydroxide and acetic acid. And again, you would get water and then you would get sodium acetate as the salt that's produced from that. So sometimes it's good to sort of think backwards when you look at a salt, try to think about where it probably came from, and you can usually answer some really important questions. The first question would be, this part of the salt, which is the sodium, came from the sodium hydroxide in most cases. So again, the relationship is this is a strong base, which means the sodium and what that means is if the acetate is relatively strong, essentially what you have is sodium acetate and water being made, right, from this original reaction. The acetate will then go and react with water and continue to react. So what's going to happen is you're going to have your acetate ion that was formed from the salt. It is going to react with water. And now sometimes people have a really hard time like, okay, I'm not really sure what's going to happen with this part of the salt. You know, how is it going to react with water? So again, this is where thinking sort of backwards can sort of help you decide what's going to happen. Again, this acetate comes from acetic acid when you think backwards about it, which means this is an acid. And its partner, which would be the acetate, would then be the conjugate base, right? So when acetate goes to react with water, it's going to base. What it's going to be as safe you get acid when it accepts that H plus from the water, it will actually produce where it came from. And the most of it will produce oxide and all that. Any questions up there? Why is it important that this salt, the acetate part of the salt, produces hydroxide ions? It is important because it is hydroxide being produced. It automatically tells you actually don't even need to do a calculation to determine that. You could actually determine that the solution will be basic because the salt will continue to react with water and it's going to produce more OH minus, and that's going to make the pH go up and become basic. Any questions on that? Also important here is If you are going to do a calculation to figure out what the pH of this solution is, you would do an ice concentration of your acid. You would do some zeros, your initial context. You put it into your equilibrium expression, which would be K2 R6, divided by our reactants. You include the water as it's a liquid, so that includes. Now, when we look at this, should this be a Ka, a Kb, Kc, blah, 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 blah? Not that one. If you're not sure, this is actually a Kb expression that you're using. So I think we talked about it earlier, but just to reiterate, when you have OH minus on the product side in any type of reaction that you are doing, and you need to do a calculation, you need to make sure that you are using a Kb value. And if you remember earlier, we saw a relationship between Kb and Ka, that the Kb times the Ka equals Kw. And you might remember earlier as well, I said there are lots of problems, or a number of problems, where they will actually give you the Ka value, but you actually need the Kb value. This right here, when you do calculations that involve salts, is that case. If you were given this problem, you would probably be given the Ka value for acetic acid, which when you actually get to the calculation part, you actually need the Kb value. So you will have to use a lot of times in salt type problems, that relationship that the Ka times the Kb equals Kw to get you to the right K value to use for your calculation. Can't tell you how many people just roll with the K value that is given to you in the problem. And out of all the places, when you're dealing with salts, probably 9 times out of 10, the K value that they give you is probably the wrong one. You shouldn't use that one. You have to convert it from Ka to Kb, or as we'll see in just a second, Kb to Ka. Questions on that aspect of it. And again, if you're not ever sure or not really sure, should you be using a Ka? Should you be using a Kb? You should always look at the product side of your reaction, which is why it's really important to be able to write these chemical equations correctly. And if you see on the product side you have OH minus, you definitely should be using the Kb when you do those type of problems. And again, if it's not given to you, but you're given the Ka, you can use the Kw to do that. So from the equation, if you correctly write it, you should see that OH minus is being generated, which without even doing a calculation will tell you that it is basic, and you need to be using that Kb value. Any questions on that there? Okay, so let's roll through this. It's going to get it all messy here, but what's behind there is essentially what we were just talking about. Now, there are salts that will produce acidic solutions. And for example, if we have, say, ammonium chloride, which I think is the example that's on this page. So if we have this salt here, again, if you sort of think about it backwards, where that salt originated from, it most likely originated from the reaction of HCl, which is hydrochloric acid, and ammonia, which is a base. And it most likely meant that the H plus would be transferred. And that is how we got our NH4Cl in this case, which would be our salt. Yeah. And I'm just going to break it up into both ions here, NH4 plus and Cl minus. which again is the same thing as it together. And again, it came from our HCl and our ammonia. And this is when we want to look at both parts of the salt and determine if anything is going to basically continue on and react with water. So the first two things that are related to is what we know is essentially what is considered a neutral salt. It will not affect the pH at all. It will not continue to react with water or anything like that. Again, the relationship is if it comes from a strong acid or a strong base, its partner will not react with water. The other two things that are related to each other is our NH3 and our NH4 plus. And this guy is a weak base, which means its partner on this side is going to be relatively strong. And again, what that means is this guy here, just the NH4 part of that salt. Again, the chloride part of that salt is neutral. It will not react with water. The NH4 plus will then react with water and continue to react. And again, if we sort of think about these things from one step before we get to the salt, the NH4 plus part came from a weak base, which means when the NH4 now, once we get this reaction, which by the way, this reaction here, when the salt goes on and reacts with water, these are sometimes referred to as because they have water reaction. And that we would expect this solution to be acidic. In addition, when we do our calculation, which again, and to be a value, and so people always get confused as to should I be using Ka here, should I be using Kb here, and again, why extremely important to be able to write these equations correctly, because the equation itself will point you in the right direction. If you see H plus or H3 on that side, you should be using a Ka value. If you see hydroxide on that product side, you should be using a Kb value. Any questions on an acidic salt? Yeah. Now, there's also another way that you could produce an acidic salt, and just go this way, and I'm just going to have those things run behind it. It's essentially what we just talked about here. Another way that you can produce, come back, an acidic salt is from a small metal. And a small metal that has a high positive charge has the ability to produce basically an acidic solution. So the example that we have here on the bottom is an aluminum that's basically surrounded by 6 waters. So I'm just going to, I'll do it here maybe, try to squeeze it in. Let's try to find some empty spot here to draw. All right, let me just draw it this way here. Okay. So basically what we got there in this really bad drawing, we got the aluminum in the center. And we essentially have 6 waters attached to it. And what I'm going to do is only the last one here, I'm going to draw out the actual water here. And when we have water, water is polar, right? Which means the hydrogen here is more positive, the oxygen is more negative. And what's going to happen is, because of this highly positive charge, kind of like what we were talking about with acid strength, this OH bond is going to become more weakened as the electrons sort of move towards that positive side. And when it does so, what it's going to do is weaken that bond to such an extent that this bond will get weak. Another water, not connected, Another water not connected to the aluminum will come by and basically be able to grab that H plus. And when it does so, what that's going to make is H3O plus, which is our hydronium ion, which is what we have going on here, basically. Yeah. And H3O plus, we would expect this to sit. And you may be wondering, looks like, all right, how do we get to that? Well, if you look up here at this badly drawn picture, we have an aluminum. We still have 1, 2, 3, 4 water. When this guy loses that, we are left with OH. So basically, we took an H plus off of one of those waters, and we produced that OH that's left over as well. So this is sort of a second way that you can produce sort of an acidic salt. It involves kind of small, highly positively charged metals. Things like +3, +2 type charges are typically what will be able to produce that. So salts can be neutral, and typically, just to summarize here, our salts can be neutral if that salt came from pretty much a strong acid or a strong base, which essentially means it will be a pH of 7. A salt could be acidic, like what we see here, if the salt came from a weak base, because when it comes from a weak base, it will then go on and produce H plus. And a salt could be basic, like we saw on the previous page, where the salt came from a weak acid. Thus, the salt would be a base and produce OH. So the choices for our salts, if the salt continues to react, then you would have to do an ice table. You want to make sure you use the right K value, and you could solve for the actual pH of that solution. Any questions on the salts or how to do that? Okay, so let's take a look at actually some of these and see if we could get to some numbers and what we would expect the solution to be if we have a salt. So I'll give you a second here on this one. So take a minute or two and see if you could calculate the pH or what the pH would be of a 0.45 molar KCl solution. So take a minute or so and decide. Okay, so let's take a look at this. So this is our salt. So again, when you're given a salt solution, you're sort of at the second step. What had produced that salt, again, is a reaction between an acid and a base, which is going to give you that water plus that salt. So if it helps you to try to decide what's going on, again, sometimes it's helpful to take the salt that you're given, and in a lot of cases, just like this problem, you're just given the salt, and try to maybe visualize or think about, excuse me, where that salt actually came from. So if we had something like KCl, it most likely came from the combination of hydrochloric acid and probably potassium hydroxide. Is probably where basically that salt came from. And when we have this salt, it breaks apart into K plus and Cl minus. So really what you want to think about is there any part of this salt that will basically go through hydrolysis, which means it will continue to react with water and do one of those type of reactions that we just saw in those previous. So if that side is partner would be the Cl minus is be also means Cl minus is going to go through hydrolysis, which also means if you don't have to any calculation, we would be 7, which is neutral. Any questions on how I got through that sort of salt there? All right, so why don't we then take a look at one where you do actually have to do a calculation, which I think should be coming up here. So let's take a look. So why don't you give this one a go, and I'll give you a hint. You do actually have to do a calculation on this one. So we're looking for what is the pH of a 0.3 molar sodium fluoride solution. The Ka value for HF is 7.2 times 10 to the minus 4. So I'll give you a few minutes, try to work through it. You should get an actual number for this one. So see what you do. Again, ICE table is sort of how you want to do it, and see what you come up with. And we'll talk about it in a few minutes. Okay, so let us take a look at this. And again, this is our salt, which is our sodium fluoride. And again, when the sodium fluoride breaks apart, it's going to break apart into sodium ions and fluoride ions. And again, if you're not really sure sort of where these things came from or if something going to go through hydrolysis, you want to think about it the step before. But really, in these problems, they do give you a pretty big hint. But if we had something like sodium fluoride, it most likely came from the combination of sodium hydroxide plus hydrofluoric acid. And again, that's going to give you your NaF and your water, right? And how did I know it was hydrofluoric acid? Because if you look in these problems, they do give you a pretty big hint. They tell you the Ka value, for example, is hydrofluoric acid, and that is usually where these things come from. So just like what we did before, the Na plus part probably came from that sodium hydroxide, and plus is group 1 or 2, which again means it's going to be a neutral salt, is not going to do anything in terms of going through hydrolysis. When we look at the F minus, it does come from this weak acid, which means this is going to be really relatively strong, and it will go through hydrolysis because of that. Now, how do I know this is a weak acid? This is the other big hint. That's a Ka value, which means it has to be a weak acid. So I would very much tell you that when you look at a lot of these problems, there's a lot of really important information that could help you answer all these questions actually sitting right there in the problem. I can't tell you how many times people just kind of overlook it and not even look at sort of the information that's given to you in the problem. So make sure you do sort of look at everything in the problem. Again, it will give you a lot of information about what's happening. So, because we know that the F minus will go through hydrolysis, we do need the reaction. So, it's going to be F minus, as again, the sodium part here is a neutral, is not going to go through hydrolysis. It will react with water. And now, the other thing that people, again, will sometimes miss is this is comes from a weak acid, which means the F minus is going to act as a base. By the way, logic also tells us that the F minus cannot act as an acid because in order to act as an acid, it needs an H and it doesn't have an H. So it can't give away something it doesn't have. So what was going to happen in this case is the F minus is going to act as the base, is going to accept the H plus. And when it accepts the H plus, it will always make where it came from, which it will make in this case hydrofluoric acid, and it will produce hydroxide as we get rid of that H plus from water. It is at this point where we should know without doing any calculation that this solution should be basic. And again, this is a very important thing to recognize because when you go and do your calculation in just a second, you'll be able to know, does my answer make sense? So, for example, if you did this calculation like we're going to do in just a second, and you got an acidic pH, by knowing the basic idea that this should be basic from the equation, you should know you screwed up somewhere. Yeah. So it's a good way to sort of check yourself as you're doing these calculations. Now, when we look at NaF, the concentration is 0.3 molar. It's a 1-to-1 relationship between the NaF and the F minus, which means the concentration of the F minus will also be 0.3 molar. So initially here, 0.3. We're going to do 0 and 0 on our ice table. We're going to do a change, which is minus x, plus x, and plus x. We're going to go and get 0.3 minus x, x, and x. Just like before, I'm not touching anything here because it is water. It's not involved in the calculation. You don't want to, put something in there that you actually don't need to use. So like normal, we're going to put this into our K value here, which is our products, which in this case is HF times OH minus divided by F minus. Again, here, our water not included. This is a K. Well, since this is OH minus and it's basic, we actually need this to be a KB value. So how you know which direction the reaction is going is much like a regular ice table. In this particular case, we're only given information about this guy. So you're only given information about your reactant. So again, it's safe to assume that the reaction is heading towards the products. The only time you might need to worry about it again is if you're given some information about everybody on both sides, the products and the reactants. But usually in a salt calculation, a hydrolysis problem, which is what these are called, usually you're just given information about the reactant or the salt. So it's 99 times out of 100, even more than that probably, safe to assume that the reaction is heading from the reactants to the products. Other questions on that? So again, the importance of being able to write these equations correctly is that you will be able to see the OH minus on this side, which originally, like we were talking about, told us that this guy should be basic when we're done calculating it. And it also is important because it should tell you you need to use a KB value. And like I was talking about earlier, just like typical hydrolysis problems, they don't give you the KB value in this case. We actually have the KA value for HF. So this is where we need to use that the KW equals KA times KB, which means the KB value in this case would be our KW, which is 1 times 10 to the minus 14, divided by our KA value, which is 7.2 times 10 to the minus 4. And that will get you 1.4 to the minus 11 as our KB value. And again, that is the number that you want to make sure that you are using in this calculation. Super often people will just throw the Ka value in there and solve it. So at this point, we now could just go to our regular process. We're going to take our 8x squared, spit that out, 0.3 minus x, and again, equaling our KB value, 1.4 times 10 to the minus 11. We're going to assume that x is equal to 0. And that would get us x squared over 0.3 equals 1.4 times 10 to the minus 11. We're going to multiply the bottom, the 0.3 to the other side, and then take the square root of it. And this will get us a x value of, x would equal, I'll just write in scientific notation, we'll go with like 2.05 times 10 to the minus 6. We do want to check it, so we would take that number and we would divide it by 0.3 and times it by 100, and you're nowhere even near 1%. So it is a good assumption. So this is good in terms of that. Yeah, so the kW is the same value that we used for kW earlier. It's the 1 times 10 to the minus 14. Yeah, so it's that same value that we use with kW equals H plus and OH minus. And it is relatively a constant. Again, it is a constant, and for the most part, most of the problems, I would say, again, probably about 99% of the problems that you come across, it's usually assumed to be at 25 degrees Celsius. Um, Technically speaking, it is a K value. So if you came across a problem that was not at 25 degrees Celsius, you technically would have to use a KW for that particular temperature. It probably would be given to you somewhere in the table or in the problem. But again, in most cases, even though it doesn't say, for example, in this problem, that it's at 25 degrees Celsius, you could probably safely assume it, unless it specifically says it's not 25 degrees Celsius. And that 1 times 10 to the minus 14 is a constant value for 25 degrees Celsius, which is probably 99% of the problems that you would come across. Other questions on that? Okay, so we're not done with the problem, right? What that X value is not the answer. It is actually the OH minus concentration. So in this case, our OH minus concentration would equal 2.05 times 10 to the minus 6. That again will not get us the pH though. That's going to get us the POH. So we want to get our POH first. And if we do that, we get something like 5.69. And again, if for some reason you thought this number was the pH, this should not make sense to you based on what you already know, that it should be basic. So again, to get to the pH, we're going to take 14 minus the POH. And that will actually get us our pH value here of 8.31. And 8.31 is basic, just like we predicted way back when here when we started the calculation. Any questions on any of those steps there? Where any numbers came from, why I put anything anywhere. Okay, so why don't you try one more? Yeah. How did I get to this reaction here? Okay, so let me just let's see here. I'm just going to write it up on top here. This is the next one, and for why I'm writing this up there, why is everybody else, or if you don't have questions on that, why don't you work on this problem and then we'll go over that. But on the top there, I will write it. I'll write how we got to that equation. So in the previous problem, we were dealing with this salt here, which it was sodium fluoride. And when that salt breaks apart, it breaks apart into Na plus and F minus. And when we look at the salt part here, it's basically two things. It's a cation and an anion. And the cation here, which is sodium, is a neutral salt. And we know that because it's group 1 from the periodic table or group 2 from the periodic table. But in all intents purposes, it most likely came from a strong base like sodium hydroxide is probably where that sodium came from. And the relationship between where it came from and its partner is an opposite relationship, which means that since the sodium hydroxide is a strong base, the sodium will be weak and will not go through hydrolysis, which is the part where it reacts with water. When we look at the F minus, it came from HF, and we know that from the actual problem. It actually has HF in the problem. And in the problem, it also gives you the Ka value for HF, which tells you right away that that's a weak acid. And the partner would be the F minus, which means it will be relatively strong. And what that means is it will go through hydrolysis, which means it will react with water. And that's how we get to that reaction you were asking about, because it's only the F minus part of that salt that originated from here that is going to go through hydrolysis. When it goes through hydrolysis, it's always going to react with water. And the way you know how it's going to react is you could use this relationship as well. Since this is a weak acid, where it came from is partner, right? When you think about acid and conjugate bases, or bases and conjugate acids, is if this is an acid, the F minus would technically be the conjugate base, which means when it reacts with water, it's going to react like a base. So it's going to accept the H plus from the water. When it accepts the H plus, just like all these salts, it will always make where it came from. So that's how we got to the HF, is when this F minus accepts that H plus. And it always, a good way to check yourself to make sure you're getting the right equation is it will always make sort of where it came from. And what is left with the water after it loses that H plus is you're left with OH minus. And again, that is how we know in that particular case that that should be a basic solution, because we generated OH minus. Questions on that? You're welcome. So work on the example up there, and you Google. Let me read your question there, and I'll get to it. Yeah, so that's the exact relationship. Is, again, as we talked about earlier, sort of when we were talking about acids and their conjugate base pairs, or bases and their conjugate acid pairs. If something comes from a strong acid or strong base, is conjugate acid or conjugate base will be what is basically considered relatively weak. And what that means is, in this application, it essentially will not continue to react with something like water, and they're considered basically neutral salts. If something comes from a weak acid or a weak base, is conjugate acid or conjugate base will be the opposite of that, like what we have here with HF, is it will be relatively strong conjugate acid or strong conjugate base. And what that means in the application of salts is it will continue to react with water. And when it continues to react with water, it either will be able to produce hydroxide, and then that solution would become basic, or it will be able to react with water like we saw a couple slides ago and produce H3O plus or H plus, and then that solution would be acidic. I think that was all of the questions, I think. Oops, sorry. All right, so take a couple more minutes and work through this one, and then we'll talk about it. Okay, so let's take a look here. So same idea. You want to think about, what's given to you in the problem. You also want to think about the salt. So we got our salt here, which is our sodium cyanide. It's going to break apart into sodium ions plus cyanide. And again, we want to look at the two parts of the salt here and determine if any of them or all of them will go through hydrolysis. So again, thinking backwards like we've been doing before, we already know sodium, which is group 1, probably came from something like sodium hydroxide. So again, it's going to be a neutral salt. It's not going to really mess up the pH or anything like that. Our CN minus most likely came from, and again, in these problems, they do give you these big hints if you look at them. It most likely came from HCN, which, if you weren't sure what it is, also another big hint is a Ka value there, which tells you it's weak, which means this will be relatively strong in the sense of going through hydrolysis. Again, when I say strong, it's not a super strong, acid or base. It's just strong in the sense of it will continue to react with water and go through hydrolysis. So that is the reaction that we want to look at before it disappears. There we go. So we're going to take just the CN minus part, as the sodium part will not go through hydrolysis. It is again going to react with water, which is pretty much what all these hydrolysis reactions will do. And again, even if you weren't sure how it's going to behave, logic would tell you that it doesn't have an H plus to donate, so it has to accept it. But again, the process to figure that out really comes from back here. HCN, which is a weak acid, would mean that the CN minus would act as a base when it does the reaction, which means in this case, much like the last one, it is going to accept the H plus from the water. And again, when it accepts the H plus, like we've been talking about, it will make where it came from, which is our HCN, and it will produce hydroxide in this case. And just like previously, without even picking up the calculator, you should already know that this solution should be basic. And again, when we do the calculation, we also know again here, we do need the KB value as opposed to the Ka value that was given to us. Any questions on how we got to that point? So again, we're just going to do a nice table here, starting with our initial concentration of 0.75. Again, it's a 1-to-1 relationship, so the concentration will be the same for both of those. We're going to leave the water alone. We're going to go minus X, and plus X. We're going to get to our equilibrium, 0.75 minus X, X, and X. This will go into our K, which is our HCN, our OH minus, divided by our CN minus. I'll answer your question in 1 second about the non a one-to-one relationship. So let me just finish this here. Again, as we talked about, because we're producing that hydroxide, we want to make sure that it is a KB value. So to answer your question, for example, whatever the salt may be, let's just say we had this made up one here of like A to B, for example. And when that would break apart, you would get 2A pluses plus B with a 2 minus. So if this was, say, 4 molar, because it broke apart into a 1-to-2 relationship, you would actually have to double the concentration. Kind of like what we did when we did like calcium hydroxide in that calculation earlier in this chapter. And from this guy to the guy at the end, it's a 1-to-1 relationship. So his concentration would be 1 times 4. So if it breaks apart into, say, a 2-to-1 relationship, you take the concentration, multiply it by 2. If it broke apart into sort of a 3-to-1 relationship, you would multiply it by 3 and so forth. So kind of very similar to, I think it was like calcium hydroxide. We did that calculation right before we did weak acids. In the notes, you had to adjust the concentration because it wasn't a one-to-one relationship. Other questions on that? Okay, so since we do need our KB value, we do want to convert it. And if we convert it, again, our KB would equal our 1 times 10 to the minus 14, which is our KW, divided by our 6.2. I really shouldn't throw things in the middle of my thing so I can see what that number says, to the minus 10 times 10 to the minus 10. And that's going to give us a KB value here of looks like 1.6 to the minus 5. So when we put this in, we will get x squared divided by 0.75 minus x will again equal our KB value of 1.6 times 10 to the minus 5. We might as well make the assumption that x is equal to 0. And I will say that in most cases, probably most of the time, your assumptions will be okay when you're doing salts. So they usually work out pretty good. So when we do that and we make that assumption, we will end up with x squared over 0.75 equals 1.6 times 10 to the minus 5. Again, multiplying the 0.75 to the other side and taking the square root. Square root action somewhere. And that gives us a x value of 3. Call it 46 times 10 to the minus 5, minus 3, I'm sorry, to the minus 3. And we do want to check it. So again, usually you're in pretty good shape on these type of problems. But again, you probably should check it just to make sure. But probably, again, 9 times out of 10, you're going to be okay on it. But if we do check it here, if we take that number and we divide it by what we're going to subtract it from, which is 0.75, and we times it by 100, again, you're like 0.46%. So the check is good, like 0.46%. So it's good in terms of that. So again, when we go to our table, we see that what we can get is our hydroxide, which does equal the X value. So that means that X equals 3.46 times 10 to the minus 3 molar, which is equal to our hydroxide concentration. That again is going to give us a POH that equals, we take the minus the log of that number, gives us a POH of 2.46. Again, if you got confused or some point and thought that that was the pH value, should not make sense to you because it would be acidic in that case. We do want to subtract our 14. And if we subtract our 14, we end up with 1154, which does make sense based on our equation and what we would expect to happen. This is a basic pH. Any questions on any of that? Or any of those steps? Okay, so this is how you work salts. Again, it's not always as it is in these two examples, obviously. It's not always going to generate hydroxide. Again, you can have an acidic salt that will generate obviously H3O plus. And really the only difference in the calculations, you would still do the ice table. You would still actually, in that case, if it did generate H3O plus, you would still have to actually convert the K value given to you, probably from a KB to a Ka value. And then, when you do solve for X, it would actually be the H plus concentration, and you could go directly into the pH equation. Any questions on any of those steps or how to calculate the pH of a salt? So again, like I said, you could have one like we talked about earlier that produces H3O plus, perform the same way, except that you do get just the H plus at the end. Just to kind of finish up our little conversation here about salts, and I'll stop the torture after this and a couple of slides here just to finish up the salt conversation. This is a much prettier picture of what I was talking about with the aluminum. Again, an aluminum that has water attached, which is pretty much what all these are. Again, one of the waters will lose an H plus to this outside water, so an H plus will come to that outside. And when it does, it's another way that you could produce an acidic solution by doing that. And this book, that's a figure, I think, from your book. Now, up to this point, when we talked about salts, only one part of the salt had the ability to go through hydrolysis. So, for example, like what we saw with our sodium fluoride, it made your sodium ion and your fluoride ion. And it was only the fluoride ion that was able to go through hydrolysis and do that reaction like we just saw. And similarly, like in that earlier one, when we were looking at ammonium chloride, for example, when it broke apart, it gave us the ammonium and the chloride. Again, here, the chloride not going through hydrolysis, but the NH4 plus could. And again, producing H3O plus in this case. Which again would make it acidic. It is possible that you could have a salt that actually both parts of the salt will go through hydrolysis. So for example, if I had this salt, which was ammonium nitrite, when ammonium nitrite breaks apart, it breaks apart into NH4 plus and NO2 minus. And where this salt most likely came from was the combination of HNO2, which is a weak acid, plus NH3, which is a weak base. And again, in this case, the H plus would come over. And that is how we would get to NH4 plus and NO2 minus, which means in this case, both parts of these guys, because they come from a weak acid and also a weak base, they both can go through hydrolysis. They both will be relatively strong in that sense and go through hydrolysis. So you would actually have both of these reactions happening at once, where this guy would donate and you would have this reaction happening where this guy would actually accept the H plus. So when you have these reactions that are occurring, how do you know sort of which one it will do? Will it do the one that where it produces H3O plus? Will it do the one where it produces OH minus? And this is where you can use the Ka value and the Kb value to compare. And whichever one is larger would be technically the reaction that would occur. So as we talked about before, since this is producing H3O plus, we would use a Ka value here, right? While when we're producing our OH minus, we would use the Kb value for this guy. And if you look at the Kb value for the anion, which is in this example, this guy, if it is larger than the Ka value for the cation, which is the NH4 plus, then the solution will be basic. It doesn't really say it up here. And you would do the calculation using the Kb value. So you would essentially do this calculation down here. Now, if the opposite is true, the Ka value is actually larger than the Kb value, then it would be more of the acidic reaction, and you would do the calculation just doing it with the Ka reaction, which would be this guy up here. If you have a Ka value that's close, almost identical to the Kb value, then it actually would be a neutral salt in that case. So if you do come across a salt where both parts of the salts have the ability to go through hydrolysis, like the example on the right, you want to look at the Ka value for the cation and compare it to the Kb value for the anion. And whichever one is larger, you would just do that calculation by itself. You would ignore the other guy. To kind of do them together, you could, but it's a lot more complicated and stuff. So usually what people will do is they'll use either the Ka value and do the calculation with that reaction, the appropriate reaction, obviously, or they will use the Kb value and do that reaction with the appropriate reaction and Kb value. And again, it will just do that. Any questions on when the salt can go through hydrolysis, both parts? Again, for our purposes, that's essentially what you'll do is you just compare those Ka and Kb values for the anion and cation. Any questions on salts or how to calculate the pH of salts or anything like that? Okay, so I did just want to get through this because technically the next lab that we're doing is pH and hydrolysis, which are salts and stuff like that. You now should probably have enough information, I believe, to work through the lab. It is not posted up yet, so I'll be honest with you. I'm going to need maybe another day or so. So I probably will post it up online in the next day or so when I get an opportunity to kind of put it together and move it over and all that kind of stuff. It will be very much like the equilibrium lab. It will be in its own module. There'll be several things that you have to go through to work through the different parts of it. There's also, I believe, a part where you have to go online and click the link. And I think you might even have to click the link sort of outside of Canvas. So it might not load inside Canvas. So you might have to kind of click one of the links as you go through the module in like your browser separately from Canvas. And there'll be sort of an online simulation where you could kind of test the pH and all that kind of stuff of some certain salt solutions. Okay, so you'll have to work through that. Now, the lab report for that one will not be due next week, so it will not be due next week or anything like that, but I will post it up probably in the next day or so in case you want to kind of get a start on it or maybe start working through it. You can. My best guess is it will not be due next week, but maybe sometime the following week, towards the end of the following week at the earliest, it might be due, or one more week after that. So it'll be due down the road a little bit, but I think we've now covered all the material that you would need to kind of go through that lab. So I will post it up. So don't freak out like it's due next week or anything like that. It's definitely not going to be due, and I'll let you know when it's due and stuff like that. Any questions on the lab, that the pH and hydrolysis lab, which was sort of scheduled for this week and into next week as well. So I think it's actually scheduled into next week as well, if I'm not mistaken. So it's definitely not going to be due next week, obviously. Yeah, so probably sometime next week, maybe. Obviously not on Tuesday, but maybe on Thursday. We could use some of that time, obviously, during lab to work on it again. So in case you have questions, you could ask probably next week. Again, towards the end of next week, probably on Thursday, because obviously on Tuesday, we're going to kind of spend the lab time to take the exam and stuff like that. Like I said, on the original schedule, I think it's actually scheduled for next Tuesday. So we may just kind of move everything down a day, as we've been doing as we kind of continue through, because I want to make sure I obviously get through the topics. So, you could hopefully go through these labs and sort of understand what you're doing, since we've hopefully covered it. So uh, I think originally it's on the schedule for next Tuesday, but obviously we're moving the exam, so we'll move that down to Thursday, when we would continue to work on the pH and hydrolysis lab. And like I said, it's not going to be due for a little while now, but I will probably post it up in the next day or so, in case you got some free time, like everybody, right? You got nothing else to do. You could, at least if you want, kind of get a jump on and stuff like that. And I definitely, when I post it up, I'll kind of figure out what the lab report will be for that. So I'll post that up as well. So I'm not 100% sure right now what it will be. I don't think it's going to be a formal lab report or anything like that. So I'll let you know what you'll have to do in terms of the lab for that. Other questions on any of that type stuff? So again, just to keep on pace, on Tuesday, as I mentioned, we will have a short lecture. I think I'm just going to probably go over the calculations involving polyatomic acids, polyprotic acids, and that will take up a little chunk of time, and then we'll break, and then that should open up the time for you to take the exam kind of during our labish time on Tuesday. And then you'll do that. And then, like I said, we'll continue on lecturing next week on this chapter. We're about halfway through. We have the really big parts coming up as well, which is buffers and titrations. It's coming up in this chapter. So they put a lot in this chapter. So we have the big topics that are coming up as well. Other questions on anything? And then obviously your lab report for the K equilibrium is due. When is that due? It's not Tuesday. I hope it is Thursday. So it's due towards the end of the week. So again, tentatively that's when it's due, at the 23rd. I'll reevaluate that and see if we want to maybe move it or not. But it's still, I think, due the 23rd, I think is when that is. Any questions on anything going on? Everybody all good in terms of what's happening? And obviously, if you still have questions on any of the labs or stuff like that, you can always email me, and I definitely will get back to you and stuff like that. And obviously, if you need any type of in-person type of stuff or help, we could obviously schedule something through Zoom as well if you sort of need that. I'm still, unfortunately, I'm still teaching 5 classes, so I'm still, busy a lot of the time. The exam is on Tuesday, 4/21. That sounds right. I'll trust you on the date. And again, it is going to cover the first 2 chapters that we talked about, which is chapter 12, which should be kinetics, and it's chapter 13, which should be equilibrium. And like we talked about before, you will not be provided any type of formulas, but any type of constants or anything like that would be provided for you. You'll be given a periodic table. I'm not sure you'll need one. And obviously those constants and values. And you will have to obviously show some work, since most of what we do is obviously, as you can see, calculations and stuff like that. So much like the quiz, you'll have to show your work and upload it when it's all said and done. Any other questions on anything going on? Okay, so again, a reminder that I truthfully am not sure if I'll get it up there today, but in the next day or so, you'll probably see the pH and hydrolysis experiment show up. And again, it's not going to be due next week or anything like that. We'll continue to work through it next week on Thursday. But in case you want to get a jump on it, you can. Other than that, if you're all good, if you don't have any questions, have a good weekend. It's Thursday, I think. Yes. And we'll see everybody next week on Tuesday. Okay, so I'm going to probably end this meeting unless you guys had any questions. You guys all good?